The metal case opened with a metallic click that echoed through the underground bunker. February 16, 1943. Beneath the sun-scorched hills of Tunisia, 5 German radio engineers gathered around a steel table in Technical Testing Station 12. The object before them was unremarkable at first glance, an American SCR-508 radio set, pulled from the wreckage of a destroyed M4 Sherman tank in the Kasserine Pass. What they were about to discover would not change the outcome of the recent battle, already won by German forces. Instead, it would reveal something far more devastating, that the war itself was already lost, and the evidence lay in something as small and precise as a quartz crystal. Ober-Engineer Klaus Hermann, formerly the chief designer at Telefunken and now serving the Wehrmacht's Signals Intelligence Branch, steadied his hands as he prepared to examine the captured equipment. For 3 years, Berlin had assured the German military that American technology was inferior, mass-produced garbage from a nation of shopkeepers who understood quantity but not quality. The official reports from the Befehlshaber der Nachrichtenaufklärung, the Signals Intelligence Command, consistently described American forces as relying on outdated equipment operated by poorly trained personnel. Yet the evidence on the battlefield told a different story. Allied units maintained communication across distances that should have been impossible. Their naval convoys never lost contact even in the midst of Atlantic storms. Their ground forces coordinated with a precision that suggested something far more sophisticated than the primitive radios German propaganda had described. Now, with the physical evidence before them, they would learn the truth. The battle that delivered this intelligence windfall had begun 2 days earlier. On February 14, 1943, General Feldmarschall Erwin Rommel launched Operation Frühlingswind, Spring Wind, a desperate counteroffensive against the Green American forces of Major General Lloyd Frendendahl's Second Corps. The German attack struck the American positions at Kasserine Pass with overwhelming force. The Afrika Korps, reinforced by elements of the 5th Panzer Army under General Hans-Jürgen von Arnim, achieved a tactical masterpiece. Inexperienced American troops, many seeing combat for the first time, broke under the assault of German panzers and veteran infantry. Within 48 hours, Rommel's forces had pushed the Americans back 50 miles, destroyed more than 100 tanks, captured thousands of prisoners, and inflicted over 6,000 casualties. It was a stunning German victory, celebrated in Berlin as proof that American forces were no match for German military prowess. But amid the wreckage of battle, German technical intelligence teams were discovering something that would undermine every assumption about American capabilities. Hauptmann Friedrich Weber commanded a signals intelligence detachment attached to the 21st Panzer Division. His orders were explicit: capture any enemy communications equipment intact. In the chaotic aftermath of the American retreat, Weber's team moved methodically through abandoned positions, searching destroyed vehicles for anything that might reveal Allied technological capabilities. East of the pass, in a crater created by the concussion of near-miss artillery shells, Weber's men found what they were looking for. An M4 Sherman tank sat with its turret blown completely off by a direct hit from an 88mm gun. The crew had died instantly, but incredibly, the radio compartment remained intact. Inside, sealed in their protective cases and still secured to their mounting brackets, were 2 complete radio sets, an SCR-508 designed for tank-to-tank communication and an SCR-510 receiver. Even more valuable, technical manuals were still present, sealed in waterproof containers. Weber immediately recognized the intelligence value of this find. He ordered the equipment transported under armed guard to the nearest German technical facility. Within hours, the radios were on their way to Technical Testing Station 12, hidden in an underground complex beneath the outskirts of Tunis. This facility housed Germany's finest radio engineers, men who had designed the Wehrmacht's own communication systems and who understood both the theoretical principles and practical realities of radio technology. Klaus Hermann had spent his career designing radio equipment for Telefunken, one of Germany's premier electronics manufacturers. He understood frequency modulation, crystal oscillators, and the intricate mathematics of radio wave propagation. He had personally designed components for the Wehrmacht's Fug series of military radios. When the captured American equipment arrived on February 16th, he assembled his best team. Specialists in frequency generation, circuit design, manufacturing techniques, and signals intelligence analysis. They approached the examination with the methodical precision that characterized German engineering. The external inspection revealed the first surprise. The American cases were housed in heavy-gauge steel cases painted in olive drab, with rubber gaskets protecting every seam and connector. The construction quality exceeded anything Hermann had encountered in German military equipment. These cases were engineered to withstand water immersion, dust infiltration, mechanical shock, and temperature extremes from -40 to +60 degrees Celsius. German military radios, by contrast, were built to more modest environmental standards, requiring careful handling and frequent maintenance to remain operational in harsh field conditions. But the real revelation came when they opened the cases. Inside, everything was standardized, modular, and clearly designed for mass production on an unprecedented scale. Every component matched the specifications documented in the accompanying technical manuals with perfect precision. There were no handwritten adjustment marks, no technician notations indicating individual tuning procedures, no variations that would require skilled assembly workers. This was equipment designed to be manufactured by the millions, assembled by semi-skilled workers in factories that could be replicated across an entire continent.
Lieutenant Hans Schreiber, a specialist in frequency control systems, began examining the crystal units that determined the radio's operating frequencies. The German military used crystal-controlled radios sparingly, reserving them for high command units and aircraft where the expense and scarcity of precision crystals could be justified. Standard Wehrmacht radios used variable frequency oscillators that required constant manual adjustment and were prone to drift. Schreiber expected to find simple, perhaps even salvaged, civilian crystals in the American equipment. Instead, he discovered something that would haunt his reports for months to come. The SCR-508 contained 10 precision quartz crystal oscillators. Each crystal was individually packaged in a hermetically sealed metal holder, precisely ground to tolerances measured in parts per million and marked with exact frequency specifications. Schreiber removed one crystal and examined it under magnification. The quartz was flawless, the electrodes perfectly aligned, the frequency marking precise and permanent. This single crystal would have required approximately 40 hours of skilled laboratory technician time to produce in Germany, yet the Americans had installed 10 of them in a standard tank radio, treating them as casually as light bulbs. Schreiber counted the crystals again, unable to believe what he was seeing. He calculated the implications in his mind. The Americans had already produced thousands of Sherman tanks. If each tank carried a radio with 10 precision crystals and similar radios were installed in jeeps, trucks, and command vehicles, the Americans were producing millions of precision crystals annually. Germany's entire crystal production capacity was approximately 200,000 units per year, and that output strained every available laboratory facility. The mathematical reality was inescapable. The Americans possessed an industrial capacity for precision component manufacturing that exceeded German capabilities by at least 2 orders of magnitude, and this was just one component of one radio type. The examination continued with increasing urgency. The team discovered that the American radio operated using frequency modulation rather than amplitude modulation that German radios employed. FM was theoretically superior. It provided static-free communication and exceptional resistance to interference, but it required significantly more complex circuitry and much more precise frequency control. German engineers had studied FM extensively and concluded it was too expensive and complicated for widespread military use. Yet here was an FM radio, mass-produced and installed in tanks operated by junior American soldiers who likely had no understanding of the sophisticated technology they were using. The circuit boards revealed automatic frequency control systems that maintained perfect tuning without any operator intervention. German radios required operators to continuously adjust multiple controls to compensate for temperature drift, component aging, and power supply variations. An experienced German radio operator spent much of his time fighting to keep his equipment on frequency. The American equipment, it appeared, simply tuned itself and stayed locked on frequency regardless of environmental conditions. Hermann began drafting his initial report to Wehrmacht High Command in Berlin. Each sentence contradicted years of intelligence assessments and propaganda claims. He documented that the captured American radio represented a level of industrial sophistication that Germany could not match with existing manufacturing infrastructure. The components required specialized factories, extensively trained workers, and quality control systems that did not exist anywhere in the Reich. More disturbing still, every aspect of the radio's design indicated it was not a prototype or limited production model. This was equipment designed specifically for mass manufacture on a scale that German industry had never attempted. Over the following 72 hours, the examination team systematically tested every function of the captured radios. They connected the equipment to German power supplies, antenna systems, and the most sophisticated test instruments available in the underground laboratory. Each test revealed new layers of American technical superiority that deepened their growing sense of professional dread. The SCR 508's transmitter produced 25 watts of clean FM signal on any of 10 selectable channels. The channel selection mechanism was elegant in its simplicity. A tank commander simply rotated a knob to select a preset crystal frequency, and the radio automatically switched frequencies, retuned all circuits, and maintained perfect transmission quality. The entire process took seconds and required no technical knowledge whatsoever. In German radios, changing frequencies required a trained operator to manually adjust multiple controls, physically replace tuning coils, and spend several minutes carefully retuning the equipment while monitoring test instruments. Many German radio operators lacked the training to perform frequency changes in the field. Range testing produced even more alarming results. Using a captured American whip antenna, the team established contact with a monitoring station positioned 20 kilometers away across the Tunisian hills. The FM signal came through with crystal clarity, without the static, fading, and interference that plagued German AM communications. Even when they deliberately introduced electrical noise from a running tank engine, the kind of interference that made German tank communications nearly impossible at times, the American receiver's limiter circuits simply stripped away the noise, delivering clean audio that German radio operators could scarcely imagine. Lieutenant Schreiber focused his detailed analysis on the crystal oscillator circuits, tracing every component, measuring every voltage, documenting the design with meticulous precision. His findings confirmed the team's worst fears. The crystal control system was not just sophisticated, it was fundamentally impossible to duplicate with German manufacturing capabilities as they existed in 1943. Each crystal oscillator required a quartz plate cut precisely to specific dimensions measured in thousandths of a millimeter. The crystals were then mounted in evacuated or gas-filled holders with electrode spacing controlled to tolerances that German factories could not consistently achieve even in small batch production, much less mass manufacture. Temperature compensation circuits maintained frequency stability across operating temperatures from -40 to +60 degrees Celsius, a requirement for equipment that might operate anywhere from the Arctic to North Africa. Schreiber calculated that producing one crystal to American specifications would consume approximately 40 hours of skilled laboratory technician time in Germany. Yet the Americans had installed 10 of them in a standard tank radio, treating them as casually as light bulbs. The question that haunted Schreiber's report was obvious. Where were the Americans finding enough trained technicians to produce millions of precision radio crystals while simultaneously fighting a two-front war? The answer, when it arrived from intelligence sources in neutral Switzerland, was more disturbing than any technical finding. The Americans were not using highly trained laboratory technicians. They had industrialized the entire crystal manufacturing process, transforming a laboratory art into a factory operation. New American factories in cities with unfamiliar names, Chicago, Newark, Fort Wayne, employed thousands of semi-skilled workers, predominantly women, operating specialized grinding machines that produced crystals with automated precision. Measurements were performed by optical comparators and electronic frequency counters, not with skilled technicians with years of training. Quality control relied on statistical sampling rather than individual inspection. The Americans had applied the mass production philosophy that built automobiles and refrigerators to the manufacture of precision radio components. The examination of the radio's receiver section revealed additional advanced technologies the German engineers had only theoretically studied. The superheterodyne circuit design was similar to German receivers, but every component was superior in measurable ways. Vacuum tubes were manufactured to tighter tolerances, with characteristics precisely matched to circuit requirements. Capacitors and resistors exhibited stability ratings that German components could not reliably achieve. The entire receiver was designed for alignment by semi-skilled technicians using simple test equipment, rather than requiring radio engineers with advanced degrees. Most troubling was the modular construction philosophy evident throughout the design. Every major subsystem, transmitter, receiver, power supply, and control unit was a separate, interchangeable module. A tank crew could remove a failed unit and install a replacement in minutes without tools or technical knowledge. Damaged modules would be returned to depot-level facilities for repair, or more likely, disposal. This approach required enormous industrial capacity to produce spare modules in vast quantities, but it meant that American tanks maintained communication capability under conditions that would leave German vehicles radio silent for days, while technicians performed intricate field repairs with inadequate tools and scarce spare parts.
The technical manuals that accompanied the radios provided yet another revelation about American industrial philosophy. These documents, printed on high-quality paper with clear diagrams and remarkably simple instructions, assumed that operators possessed minimal technical training. Operating procedures were reduced to numbered steps that anyone literate could follow. Troubleshooting guides used decision trees that required no understanding of radio theory. Maintenance instructions specified exact replacement intervals for components based on operating hours, rather than relying on operator judgment or periodic inspection. Hermann recognized that these manuals revealed as much about American military doctrine as the radios themselves. The Americans had accepted a fundamental premise that German military tradition rejected. Frontline soldiers were not technical specialists and should not be required to become such. Rather than training every radio operator to understand electronics theory, circuit design, and repair procedures, the Americans had engineered equipment that any reasonably intelligent soldier could operate and perform basic maintenance on using simple, clearly documented procedures. This approach required more sophisticated and expensive equipment, but it solved the fundamental military problem of maintaining reliable communications under combat conditions with personnel who had minimal specialized training. It also meant that radio operators could be replaced without catastrophic loss of communications capability, a crucial advantage in sustained combat operations where casualties among specialists could cripple a unit's effectiveness. German radios, in deliberate contrast, required skilled operators who understood radio theory, could perform complex field repairs, and possessed the technical judgment necessary to keep temperamental equipment functioning in adverse conditions. These operators required 6 months of intensive training and years of experience to become truly proficient. They were irreplaceable assets, and when they were killed, wounded, or captured, their equipment often became useless to whoever inherited it. By the end of the 3rd day of examination, the team had documented every circuit, measured every component, tested every function, and analyzed every design decision evident in the captured American radios. Their report to Wehrmacht High Command exceeded 200 pages of technical analysis, supported by photographs, detailed circuit diagrams, and component specifications. The conclusions were professionally devastating. The Americans possessed radio technology that was 5 to 10 years ahead of German equipment in critical areas. Frequency modulation, precision crystal control, automatic frequency stabilization circuits, and modular construction represented fundamental advantages that could not be overcome through superior tactics, better trained operators, or incremental improvements to existing German designs. These were not evolutionary advances. They represented a fundamentally different approach to military communications engineering. More critically, every aspect of American radio equipment was designed from inception for mass production on an industrial scale that Germany had never attempted. The entire design philosophy reflected an industrial capacity and organizational approach that Germany simply did not possess and could not develop within any time frame relevant to the current war. Hermann's report estimated that Germany would need to construct at least 30 new specialized factories, train more than 50,000 additional workers, and invest resources equivalent to the entire annual Luftwaffe procurement budget merely to match current American radio production capabilities. Even then, Germany fundamentally lacked certain raw materials, particularly high-quality quartz crystals and specific rare elements required for precision components. Many of these materials were sourced from regions now firmly under Allied control, including Brazil's quartz deposits and North American mineral resources. The conclusion was professionally inescapable and strategically devastating. American industrial capacity had rendered technological superiority militarily decisive. Germany could design equipment equal to or even superior to American models in theoretical capability, but German industry could not manufacture such equipment in quantities sufficient to matter on the battlefield. The war would ultimately be decided not by which side possessed better engineering knowledge, but by which side could transform that knowledge into millions of units of functioning equipment delivered to frontline forces. The report reached Berlin on February 25, 1943. It was immediately classified Geheime Kommandosache, most secret, and distributed to fewer than a dozen senior officers in Wehrmacht High Command and the Reich Ministry of Armaments. The response was institutional silence. No new factories were authorized, no crash programs were initiated, no strategic adjustments were made to account for the American advantages. The implications were simply too devastating to acknowledge publicly, and privately, senior German leadership understood that the industrial gap could not be closed while simultaneously fighting the Soviet Union, defending occupied Europe, and supporting Italy's collapsing position in the Mediterranean. But the work of Technical Testing Station 12 was far from complete. Over the following months, additional American equipment fell into German hands as Allied forces gradually pushed Axis armies back across North Africa. Each captured example provided new evidence of American technical and industrial superiority. An SCR-300 radio, the famous backpack walkie-talkie that would become iconic in later war footage, revealed FM technology miniaturized into a portable unit weighing only 18 pounds, yet providing reliable voice communications up to 5 kilometers. Comparable German portable radios weighed over 40 pounds for the radio alone, plus an additional 20 pounds for external battery packs, and achieved barely half the effective range.
An SCR-299 captured during the invasion of Sicily in July 1943 stunned the examination team with its sophistication. This mobile long-range communication station, installed complete in a truck with integrated power generator, produced 350 watts of transmitter power across a frequency range from 2 to 18 megahertz. The transmitter featured crystal-controlled stability and could change frequencies in minutes rather than the hours required for comparable German equipment. The associated receiver employed a super heterodyne design with 15 vacuum tubes, multiple conversion stages, and a crystal filter for improved selectivity. German long-range communications equipment of similar capability existed, but only in fixed installations requiring building-sized antenna systems and dedicated power plants providing stable electrical supply. The Americans had packaged equivalent capability in a vehicle that could be driven anywhere roads existed, set up by a small crew in approximately 1 hour, and operated reliably under field conditions. The philosophical difference was stark. German equipment assumed the battlefield would adapt to technological requirements. American equipment was designed to function wherever the battlefield required. Each examination revealed the same fundamental pattern that had emerged from the first SCR 508 in Tunisia. American equipment was engineered specifically for operation by minimally trained users, mass production by semi-skilled workers, and field maintenance following simple documented procedures. German equipment required skilled operators, hand assembly by trained technicians, and field repairs by electronics specialists. One design philosophy scaled naturally to millions of units and global deployment across every theater of war. The other philosophy could not scale beyond the limited capacity of Germany's technical workforce and specialized manufacturing infrastructure. The technical intelligence reports flowing from Tunisia, Sicily, and later Italy documented not merely individual radio sets with impressive specifications, but an entire communications philosophy that pervaded American military doctrine. American forces maintained constant voice contact from squad level to theater command through multiple layers of interconnected radio networks. Platoons operated SCR 536 handheld transceivers for short-range tactical communication. Companies employed SCR 300 backpack radios for company-to-battalion coordination. Battalions used vehicle-mounted SCR 508 and SCR 608 sets for battalion-to-regiment communications. Regiments operated SCR 193 and SCR 299 long-range equipment for regiment to division and beyond. Critically, all American radios employed compatible frequency systems and genuinely interoperable equipment standards. A forward artillery observer with an SCR 300 could directly contact an artillery battalion 20 kilometers distant using an SCR 608 because both radios operated on FM using compatible frequencies with crystal-controlled stability. German forces, in stark contrast, operated multiple incompatible radio systems, each requiring different frequencies, different modulation types, and completely different operating procedures. Establishing communication between different German units often required relay stations or physically carrying messages because the radios simply could not talk to each other. By summer 1943, German signals intelligence had documented over 50 distinct American military radio types, ranging from handheld transceivers to sophisticated airborne command sets. Production estimates derived from captured serial numbers and intelligence reports from neutral countries suggested that American factories were producing more than 100,000 military radio sets monthly. German production, encompassing all services and all types of communications equipment, peaked at approximately 15,000 units monthly, and that production level proved impossible to sustain as Allied bombing intensified. The examination teams began analyzing captured American manufacturing documentation, technical orders, parts lists, maintenance manuals, and depot-level repair procedures. These documents revealed the industrial infrastructure supporting American equipment in ways the radios themselves could not. Components were rigorously standardized across multiple radio types. Vacuum tubes employed common base configurations allowing physical and electrical interchangeability. Crystals followed standardized holder designs. Even mundane items like screws, nuts, and bolts adhered to unified thread standards that guaranteed interchangeability across equipment types. This standardization philosophy meant that American factories could shift production between different radio models without extensive retooling. A manufacturing plant producing SCR 508 transmitters could transition to SCR 608 units by changing only specific fixtures and component inventories while retaining the same production machinery and trained workforce. Parts salvaged from one radio type could often be used to repair other models. The entire system was intentionally designed for manufacturing flexibility and industrial scale. German manufacturing employed the opposite philosophy. Custom components were designed for each equipment type to optimize performance for specific applications. The Fug-10 tank radio shared virtually no components with the Fug-10 aircraft radio, despite fundamentally similar electrical functions. Each radio type required dedicated production lines, unique testing equipment, and specialized spare parts inventory.
Changing production priorities required months of retooling, retraining workers, and redesigning manufacturing processes. Oberengineer Hermann transferred to a larger technical intelligence facility in northern Italy by autumn 1943. He spent increasing amounts of time analyzing American manufacturing methods and industrial organization rather than merely examining equipment. His reports to Berlin evolved from technical assessments of radio circuitry to strategic warnings about relative industrial capacity. He methodically documented the American electronics industry's explosive wartime growth, compiling intelligence from neutral country sources, captured documents, and analysis of equipment serial numbers. Companies with unfamiliar names had transformed seemingly overnight into massive military contractors. Galvin Manufacturing, which would later rename itself Motorola, had evolved from a small Chicago radio manufacturer into a major military supplier, producing hundreds of thousands of units annually. Hallicrafters, previously known primarily for amateur radio equipment, was manufacturing sophisticated military receivers in quantities exceeding total German radio production. Western Electric, the manufacturing subsidiary of Bell Telephone System, operated enormous factories employing tens of thousands of workers, producing crystals, vacuum tubes, and complete radio systems. These companies had scarcely existed as military suppliers before 1941. The Americans had created an entire military electronics industry in less than 2 years by systematically converting civilian factories, rapidly training new workers, and applying mass production techniques originally refined in automotive engineering and consumer appliance production. Detroit automotive engineers had designed radio production lines operating with the same efficiency and scale as automotive assembly plants, treating precision electronics like mechanical components subject to identical manufacturing discipline.
The German radio industry, centered in Berlin, Munich, and Hamburg, remained organized fundamentally as it had been in the 1920s. Small, specialized manufacturers produced equipment using skilled craftsmen working in relatively small batches. Production quantities were measured in hundreds of units per month, not thousands per week. Quality control depended on individual inspection and hand adjustment by trained technicians, not on statistical process control and automated testing systems. Hermann's comprehensive December 1943 report to the Reich Ministry of Armaments carried the stark title, The American Radio Industry, an assessment of industrial capacity and strategic implications. It documented American electronics production in devastating statistical detail. United States industry was producing annually what would require Germany 20 years to manufacture at current capacity. The gap was not merely technological, it was industrial, organizational, and philosophical. German engineering remained superior in many theoretical respects, but American industry had solved the practical problem of translating engineering knowledge into millions of units of functioning equipment. The report estimated that American factories possessed sufficient capacity to produce enough military radios to fully equip 1,000 divisions, though the Americans actually fielded only approximately 90 divisions throughout the war. This enormous surplus capacity meant that American forces operated with effectively unlimited replacement equipment. Damaged radios were not painstakingly repaired in field workshops, they were simply replaced with new units from vast depot stockpiles. Outdated models were retired to training units and replaced with improved designs. Newer, more capable equipment was continuously introduced, not as limited production prototypes, but as mass-produced systems distributed across entire theaters of operation. German forces, meanwhile, carefully husbanded every radio as an irreplaceable asset. Field technicians performed delicate repairs under combat conditions, cannibalizing components from damaged sets to keep others operational. Replacement equipment arrived irregularly, if at all, and units learned to make do with whatever communications capability they could maintain. Newer designs remained in limited production because retooling factories would temporarily reduce output of existing models, and that temporary reduction could not be tolerated given chronic equipment shortages. The crystal supply situation exemplified the industrial disparity. By late 1943, German quartermasters estimated they required 5 million precision crystals for existing radio equipment and planned upgrades.
Domestic production capacity stood at approximately 200,000 crystals annually, and that production strained every available laboratory facility. Even if Germany devoted enormous resources to expanding crystal manufacturing, achieving the required 5 million units would require more than 2 decades at maximum feasible production rates. The Americans, according to intelligence estimates compiled from multiple sources, were producing 30 million crystals annually. They had solved the quartz supply problem through multiple parallel efforts, discovering and exploiting deposits in Brazil, developing mining operations in Arkansas, and even conducting experimental research into synthetic crystal growing. American crystals were not merely abundant, they were superior in quality, achieving frequency stabilities that German laboratories could barely measure with their most sophisticated instruments, much less manufacture in production quantities. The examination of captured American test equipment revealed yet another dimension of the industrial superiority. American radio factories employed automated test sets that measured frequency, power output, modulation quality, and receiver sensitivity in seconds. These sophisticated testers were themselves complex electronic instruments, yet they were produced in sufficient quantities to station dedicated test equipment at every assembly line workstation. Workers with minimal training could operate these testers by following simple procedures, ensuring consistent quality without requiring engineering expertise. German factories employed manual testing procedures requiring skilled technicians spending several minutes per unit. Testing became a production bottleneck that limited manufacturing rates regardless of component availability. One captured American test instrument, a Measurements Corporation signal generator standard in U.S. factories, became a prized possession at the technical facility. This single instrument could generate precisely calibrated signals across the entire radio frequency spectrum. It cost approximately $300 to manufacture in American factories. The equivalent capability in German facilities required a laboratory room filled with separate oscillators, attenuators, and frequency meters, costing thousands of Reichsmarks and requiring constant calibration by skilled engineers. By early 1944, the cumulative message from technical intelligence was clear, terrifying, and growing more severe with each passing month. American communications superiority was absolute, irreversible, and expanding. Every month, American factories produced more radios than Germany possessed in its entire military inventory across all services. Every captured example demonstrated incremental improvements, design refinements, and manufacturing sophistication that Germany could not hope to match while simultaneously fighting existential battles on the Eastern Front and defending against inevitable invasion in the West. The introduction of American radar systems in late 1943 and early 1944 drove the message home with even greater force. Radar represented radio technology pushed to its ultimate extreme, employing microwave frequencies, pulse techniques, and sophisticated signal processing that demanded the highest levels of manufacturing precision and component quality. The Americans were mass-producing radar sets for ships, aircraft, and ground installations with the same industrial efficiency they applied to voice communications radios. A captured SCR-584 fire control radar examined in March 1944 demonstrated technical capabilities that German radar scientists had only theorized about in academic papers. This massive system operated at the extremely high frequency of 3,000 MHz, employed a precision tracking mount with automatic target-following circuits, and achieved accuracy sufficient to direct anti-aircraft guns to destroy enemy aircraft with devastating effectiveness. The complete system weighed over 10,000 pounds and required a dedicated vehicle for transport. Yet American factories were producing them by the hundreds, installing them at anti-aircraft batteries throughout liberated Europe and the Pacific. German radar development had focused necessarily on longer-wave systems operating below 1,000 MHz because German industry could not manufacture the specialized vacuum tubes, particularly magnetrons and klystrons, required for microwave operation. These exotic tubes demanded precision machining measured in thousandths of an inch, exotic materials like tungsten and molybdenum, and manufacturing techniques that Germany simply did not possess. Even when German scientists designed advanced microwave radar systems on paper, they could not be manufactured because the critical components did not exist in German production. The systematic examination of captured American equipment continued relentlessly through 1944 as Allied forces advanced up the Italian peninsula and prepared for the decisive invasion of France. Each new example added to the mounting evidence of American technical superiority. Improved radio models appeared with regularity. The SCR-694, introduced in mid-1944, provided frequency modulation tank communications with increased range and reliability over earlier models. The SCR-619 aircraft radio offered hundreds of crystal-controlled channels and near-instantaneous frequency switching, allowing pilots to communicate with multiple ground stations and other aircraft without manual retuning. Most significantly, American equipment reliability improved continuously and systematically. Early production SCR-300 radios had experienced occasional problems with moisture infiltration and battery contact corrosion. Captured examples from late 1944 showed redesigned cases, improved environmental seals, and modified circuits that completely eliminated these issues. The Americans were not merely building equipment, they were continuously improving designs based on systematic analysis of field experience and incorporating lessons learned directly into ongoing production. This closed-loop improvement cycle was possible only with an industrial base capable of implementing design changes across multiple factories simultaneously without disrupting production schedules. German equipment quality, in tragic contrast, often degraded as the war progressed. Material shortages forced substitution of inferior components, aluminum replacing copper, paper capacitors replacing ceramic ones, lower-grade vacuum tubes replacing precision models. Skilled workers were conscripted into combat units to replace mounting casualties, leaving factories staffed with increasingly inexperienced personnel. Quality control suffered as factories focused desperately on meeting production quotas regardless of reliability concerns. Radios that should have functioned reliably for years began failing after months of field service. By the time of the Normandy invasion in June 1944, German technical intelligence had documented the complete and devastating picture of American communications superiority. Allied forces landing on French beaches carried more radios collectively than the entire German Wehrmacht possessed across all fronts. Every Allied company maintained radio contact with battalion headquarters. Every battalion could reach division command reliably. Artillery forward observers directed fire accurately from dozens of kilometers away because their radios never lost contact with fire direction centers. Communications worked because American industry had provided equipment in quantities sufficient to ensure redundancy, reliability, and operational flexibility. German commanders attempting desperately to coordinate defenses against the invasion found their communications networks breaking down catastrophically under the combined stress of Allied jamming, artillery bombardment, and the fundamental chaos of mobile warfare. Radios that worked acceptably on test ranges failed under combat conditions. Crystal oscillators drifted off frequency in the Norman summer heat, rendering communication between units impossible even when both radios were functioning. Battery-powered sets exhausted their power supplies quickly because replacement batteries were unavailable, trapped somewhere in the disintegrating logistics network. The carefully planned communications infrastructure that German doctrine assumed would exist simply ceased functioning under sustained combat stress. The technical reports flowing back to Berlin became increasingly desperate in tone. Ober-Engineer Hermann, now attached to Wehrmacht operations staff, wrote in August 1944 that Germany had irrevocably lost the electronic war. American jamming equipment, radio direction finding systems, and signals intelligence capabilities allowed Allied forces to locate and target any German radio transmission within minutes of initiation. German codes, despite periodic changes, were systematically broken through a combination of cryptalysis and traffic analysis. Movements of German units were tracked precisely through radio communications patterns even when message content remained encrypted. The final collapse of German radio communications came in late 1944 and early 1945 as Germany's remaining industrial infrastructure disintegrated under relentless Allied strategic bombing. Factories producing communications equipment were deliberately targeted for destruction. Telefunken's Berlin facilities were devastated in November 1944 by a massive American daylight raid. Lawrence production plants in Stuttgart were bombed repeatedly throughout winter 1944-1945. The critical crystal production facility in Sudetenland fell to Soviet forces in January 1945, eliminating Germany's last significant source of precision frequency control components. By March 1945, German radio production had essentially ceased entirely. Existing equipment continued functioning through the increasingly desperate efforts of field technicians who cannibalized components from damaged sets and improvised repairs with whatever materials could be found. When a headquarters radio failed, commanders simply lost contact with subordinate units, sometimes for days. When tank radios broke down, armored formations devolved into isolated groups of vehicles, incapable of coordinated action. The communications infrastructure that modern warfare absolutely required had ceased to exist in any meaningful form. The Americans, in almost surreal contrast, continued improving equipment even as final victory approached. New radio models introduced in early 1945 offered enhanced range, additional channels, and improved reliability over previous versions. Production continued at full industrial capacity, not because more radios were actually needed. American supply depots were overflowing with excess equipment by this point, but because the vast industrial machine created in 1941-1942 could not easily be shut down or converted to peacetime production while combat operations continued. When Germany surrendered unconditionally on May 8, 1945, Allied occupation authorities began systematically cataloging captured German documents and equipment. Among the materials discovered in salt mines and underground archives were the technical intelligence reports from Tunisia, Sicily, and Italy. The meticulous documentation of captured American equipment that Hermann and his colleagues had produced. American technical teams searching through German facilities in summer 1945 were genuinely surprised to discover how thoroughly German engineers had examined captured American radios and how accurately they had assessed American capabilities. One particular report, written by Ober-Engineer Klaus Hermann in April 1945 as Soviet forces closed inexorably on Berlin, served as his final professional testament. He wrote with remarkable clarity that Germany's defeat had been mathematically inevitable from the moment German engineers opened the first captured American radio in Tunisia in February 1943. The precision frequency crystals, automatic stabilization circuits, and modular construction philosophy revealed an industrial approach to warfare that Germany fundamentally could never match. The Americans had industrialized war itself, applying mass production techniques to every aspect of military equipment. Hermann's conclusion was stark and historically significant. Future wars would be decided not by superior soldiers, better generals, or more sophisticated tactics, but by industrial capacity to produce high-technology equipment in overwhelming quantities. Germany had fielded excellent soldiers, competent commanders, and adequate tactics. What Germany lacked was an industrial infrastructure capable of matching American production. This deficiency was most starkly visible in something as deceptively simple as a radio crystal. Precision quartz ground to exact specifications by teenage workers in American factories producing millions of units annually, while German laboratories struggled to manufacture thousands. The story of German engineers examining captured American radio equipment represents far more than a technical curiosity from World War II. It illuminates the fundamental transformation of warfare from an activity determined primarily by tactics, training, and courage to one determined by industrial capacity, technological sophistication, and manufacturing efficiency. The frequency crystals that so impressed Hermann and his colleagues were not magical. They were precision engineering, certainly, but more importantly, they were precision engineering scaled to genuine mass production. American industry had learned to produce millions of units to identical specifications, an achievement unprecedented in industrial history. This capability, developed initially for radio crystals, extended systematically to every aspect of military equipment and eventually to every category of manufactured goods America produced. The principles that German engineers identified and documented, design for manufacturability, component standardization, operator simplicity, systematic quality control, became the foundation of modern industrial practice worldwide. Those lessons, purchased at the cost of Germany's defeat, shaped manufacturing philosophy for generations. In the final analysis, the small quartz crystal that Lieutenant Schreiber first examined in February 1943 represented a symbol of the Industrial Revolution in military affairs. It represented the moment when victory ceased being determined primarily by battlefield prowess and began being determined by factory output. The German engineers who systematically examined American equipment in underground facilities across occupied Tunisia and Italy were not merely analyzing radios. They were documenting the future of warfare, technology, and industrial organization. Their detailed reports, classified and filed away during desperate years of combat, eventually became historical documents explaining not just why Germany lost, but how industrial capacity determines outcomes in modern warfare. The quartz crystal, that precisely ground quartz oscillator produced by young American workers in quantities Germany could never approach, told the entire story in miniature. Industrial warfare demands industrial capacity. Without it, no amount of tactical brilliance, technological innovation, or individual courage can achieve victory. That lesson, learned by German engineers examining American equipment in 1943, remains as relevant today as it was 80 decades ago. The side with greater capacity to produce sophisticated technology in overwhelming quantities will ultimately prevail. The mathematics of modern warfare, written in frequency crystals and circuit boards, admits no other conclusion.